So we have this equation, delta d delta over dx is equal to 140 divided by 13 mu divided by rho u infinity. Now integrate this equation, we will get delta, because delta is a variable here, delta is function of x. So delta square is equal to 280 divided by 13, because it will become delta square divided by 2, this 2 will go here and this will be 280 divided by 13 mu x divided by rho infinity plus some constant of integration. If we assume that boundary layer starts growing from the leading edge, then when x is equal to 0, delta is equal to 0, so c becomes 0. In that case, this equation can be written as delta over x square, this thing, and ultimately we will get this equation. With the help of this equation, we can find out the boundary layer thickness at any location. So if we know the value of x at which point we want to know, so we know what is the x is the distance measured from the leading edge of flat plate. This is the, we have to keep this thing in mind, that this is the problem we are solving for flat plate. So delta over x is equal to 4.64 divided by root of Rex. What is Rex? Rex is equal to rho u infinity here, generally it is written as rho u, multiplied by x divided by mu is known as Rex. So at a given location we know the value of Rex and we can find out delta over x, and with the help of this we can find out delta. Please keep this thing in mind that this is the not the general formula for calculating the boundary layer thickness. In any exam, if you have different velocity profile than selected in this problem, when we have solved this problem, then we had assumed this velocity profile. So whatever solution we are getting for finding out the velocity boundary layer thickness at different location, for this velocity profile only this relationship is valid, delta over x is equal to 4.64 divided by root of Rex. If we have different velocity profile, then this delta over x will be different, right? So with the help of this equation we can give answer to this question, that what is the velocity profile or boundary layer thickness at a given location, and we can find out the boundary layer. Now next question is how to get drag. This drag is calculated with the help of concept of skin friction coefficient. Skin friction coefficient, if you can recall the chapter of pipe flow, at that time we brought this term CFX, skin friction coefficient. Since this is a CFX, so it means it is a local skin friction coefficient, is equal to tau w divided by 1 over 2 rho infinity square, right? So what is the need of defining? We have already understood in case of the dimensional analysis that generally we define several dimensionless numbers so that the experimentation becomes easy and its interpretation also becomes easy. So instead of directly calculating tau w, we are going to calculate for CFX, local skin friction coefficient, which is defined as tau w. Our aim is to find out tau w basically. If tau w multiplied by area, we will get drag. Tau w divided by 1 over 2 rho infinity square. This is a dimensionless number. So we have calculated tau w, right? So substitute that tau w. This is the tau w is equal to 3 by 2 mu infinity divided by delta. Substitute this tau w in this equation and we will get CFX. So this CFX is equal to, ultimately we will get this value for which velocity profile? For velocity profile which we have selected for solving this problem. CFX is equal to 3 divided by 4.64 Rex raised to minus half. This is a local skin friction coefficient. This will give us only local shear stress, but our aim is to find out average, basically average shear stress. So how do we get average shear stress? Average skin friction is defined CF bar. This is a average skin friction drag. This average skin friction drag is equal to tau average divided by 1 over 2 rho u square. This is tau w divided by 1 over 2 rho u infinity square, and if we have a average, then it will give you average shear stress. So if we can get average shear stress acting on the wall, acting on the flat plate, so average shear stress, what is average shear stress on this flat plate? It may be varying. Here we have different shear stress, 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 but our aim is to find out the total drag. So for calculating the total drag, if we can calculate the average shear stress, then average shear stress multiplied by area will give you average drag or total drag due to the boundary layer. So what is average skin friction coefficient? Cf bar is defined as 1 over L, where L is the length of the flat plate in the direction of the flow, 1 over L integral 0 to L Cf x dx. In the integration we have studied that how to get the value of average with the help of local value. So substitute the value of Cfx in this equation and then integrate it, we will get this value. Cf bar average skin friction coefficient is equal to twice of 0.646 REL raised to half. What is this value? If we compare with this, Cfx is equal to 0.646 Rex raised to half. Here we have 0.646 REL raised to half. It means that this is the local skin friction at the trailing edge at this point.